Good morning, everyone, and a very warm welcome to this, which is the first of the Bolin Centre's seminar series this year. And this year, the first seminar series is hosted by Research Area 2. And I'm going to hand over to Frida, as one of the leaders of Research Area 2, who's going to present our speaker. Now, some of you might wonder why the microphone isn't working. It is working. It's not for you to hear. It's because it gets recorded into the, because the lecture will be streamed. And when you're answering questions, you'll be asked to hold the microphone to your mouth, and it will feel strange because it's not doing anything, but it is doing something. Trust us. Okay? So, Frida.
Thank you. So I'm Frida Bender, and I'm Research Area 2 leader together with Matt Salter is here. And it's my pleasure to introduce today's guest and speaker, Dr. Heike Wex from the Leibniz Institute for Tropospheric Research, also known as Tropos, in Leipzig. Heike, she's originally from Germany, and she started her physics education in Gießen, where she got her diploma, and I have to read here, semiconductor gas sensors,
yes.
which is quite far from what she's doing today in the atmospheric path that she came on later. But after spending some time in the US at the Rice University in Texas and also some time in Bulgaria, she ended up in Leipzig where she got her PhD in 2002. And at Tropos she has worked a lot with the LACES, the flow tube there that we're probably going to hear more about, but it's a cool thing where you can look at aerosol cloud interactions in a controlled environment. So she's worked with hygroscopic growth and droplet formation and now ice nucleation. And in addition to all these scientific achievements that you may know her for, some of you may also know her for her organizational skills in organizing the ICCP in Leipzig a few years ago. And after today's talk, we will all, I think, know her for being the one who taught us all we need to know about ice nucleation. So go ahead, Heike.
Okay, yeah. So thanks for the introductory words to both of you, and welcome to my audience. I'm really honored to be able to speak here, and thank you for inviting me. And I hope I will not disappoint you, because in the end I had been told that I would attract a crowd with different scientific backgrounds, so I will actually really keep it very basic. I will not deep into anything. I will give you just glimpses of little bits and pieces, and I don't want to go into LACES too long actually, but anyway, I will at least mention it. So, overview, I will give a short introduction and then a little bit of a historical overview and talk a little bit about measurements, not too much. And then I will go about new findings in more detail. That's about a lot of laboratory studies. And in the end, I will talk about atmospheric ice nucleation particle concentrations. So let's start with the introduction. There I want to say a very few words about atmospheric aerosol particles first. Then I want to tell you a little bit about homogeneous and heterogeneous freezing, just to set the ground for all of us. And then I will tell you a little bit on how a mixed phase cloud actually works. So atmospheric aerosol particles. I'm not sure if you all know that. I think you do, that we have aerosol particles all around us here, always, everywhere. And there are different sources. We can have primary particles in the air that are emitted directly. For instance, if we have a dust storm, or whenever you have whitecaps in the ocean, you have little gas bubbles that explode and put sea spray in the air. So that's a primary particle then. Anything that burns or volcanic eruptions put in particles in the air directly. But there are things that also emit precursor gases into the air. For instance, also when something's burning, also gases are emitted, also by volcanic eruptions, algal blooms, or also vegetation. These gases can form particulate matter that form particles themselves or attach to other particles. Some of these processes are natural, others are anthropogenic. So all I want you to remember from that slide is we have these particles and it's a big mixture of things. That's already all, not more about that in that talk. So now the ground about freezing. We all do know that below 0 degrees Celsius ice is the thermodynamically stable phase. I mean, I'm here at the right time of the year. You all can see that outside. But how would water go into that phase? That's a crystallization process, and I know that at least one person in the room knows about crystallization. I guess more of you do. So imagine you have a drop of only water molecules, that's liquid, and you cool that down. So what you have to do is that you have to start a nucleation. And what that graph kind of shows you is the free energy that you have when you form a little clump of crystal, ice in that matter, so water molecules arranged in an ice-like manner. So that red curves gives you the free energy for forming the surface area, and that gives you the free energy for forming the volume. So add these two together, you get the blue curve. And what that tells us, if you have in your ball of water a little clump of ice, and it is, let's say, a nanometer or so in radius, and you want to add one more molecule, you have to put energy into the system to get that there. And after a certain size, when it's above 1.5 or 2 nanometers large, at minus 30 degrees at least, by adding the next molecule, the thing will just gain energy. So from here on, if we manage to make such a small ice nucleus in a droplet, the whole droplet will freeze through. But before you get that critical embryo, freezing will not occur. And that blue curve I told you is at minus 30 degrees Celsius. It's that curve here. So that curve is temperature dependent. It's at different temperatures. And you see that little ice drum that you have to form before the whole drop freezes through gets larger and larger and larger the warmer it gets. And already the size that you need for at minus 30 degrees Celsius doesn't occur randomly in nature by chance on observable time scales for the atmosphere. That means the other way around. At roughly below minus 38, minus 40 degrees Celsius, that little ice drum that you need before the whole droplet freezes through is small enough that it can occur randomly. It just assembles, some water molecules assemble, freezing occurs. But above that, we do observe ice at these temperatures between 0 and minus 38 degrees Celsius in the atmosphere, but it cannot be that type of pure water freezing. You need to have a surface that supports that freezing. And this is these ice nucleating particles. They are needed above minus 38 degrees Celsius to stabilize or arrange water molecules so that the nucleation process can start. So that means that is then heterogeneous freezing, and the nucleation is aided by some kind of catalyst. That is how you can think of that. And there are different heterogeneous freezing processes. I will not go into that in detail because it just takes too much time, but for those of you who are familiar with that, I want to at least give a few hints on what the newer developments or insights into these things are. So deposition ice nucleation is ice deposits on a surface directly from the vapor phase. That has been reported in many, many older lab studies. However, that view has been challenged by Claudia Marcolli in 2014. As she said, even for those surfaces that people looked at, there might be little caveats in there in which water condenses more readily, and then it could all just have been condensation and immersion freezing. So that is questions if that deposition ice nucleation as such without liquid water exists. But it exists anyway in the atmosphere only where relative humidities are below 100%, if at all. Contact freezing is you have a supercool droplet and an ice nucleating particle and they hit. That is a very effective mechanism. But for the atmosphere, it might just be that these collisions occur too seldom for the process to be really important. That is under debate, and it also depends on the conditions. Now condensation freezing and the last one, immersion freezing. If you go into literature in the old days, there was only one of the two mentioned, and then suddenly they split up. If you look at different papers, they are split up or described in different ways. It always confused me. I summarized kind of that in a paper in 2014, so you could go and look up the details. But the thing is that you might say in both cases you have liquid water around a particle. Sometimes some people say it depends on how much it is, how long it is, at which temperature. As I said, it's not very well defined. You have liquid water in both cases, and you can describe this similar to this. In this case, you have diluted water around your particle. In this case, you have maybe more concentrated water around your particle, a little less of that. So it can just be described as immersion freezing and concentrated solutions. So you have to just acquire a freezing point depression there. So that one, I now put a red box around immersion freezing because what I want to focus on in my talk is really immersion freezing. And that is thought to be the most important heterogeneous freezing process in mixed phased clouds. They occur at temperatures between 0 and minus 38 degrees Celsius. These clouds are these are the clouds where you can have liquid water and ice at the same time. And warmer clouds, there's no ice. In colder clouds, it's all ice. So here I come to the part where I want to tell you about such a mixed phased cloud. What happens when a cloud forms? Down here, I do show our zoo of aerosol particles. Well, not too many, but you know there are much more than 4 out there. So as an air parcel rises, it cools because it expands. And at a certain height, you will reach a relative humidity of just a little bit about 100%. What then happens is that some particles, not all, can be activated into a cloud droplet. That's another kind of nucleation process, so some particles just acquire water and become a large droplet very fast. That typically happens in the first some 10-ish meters of a cloud, depending on the updraft velocity. There's a maximum in supersaturation, and then all the water vapor is gone to the particles that can activate, and the others just stay unactivated, interstitial aerosol. Those particles that can activate, we call cloud condensation nuclei, CCN. You don't have to remember that term, I'm only using it on that slide. And the word I want to say here is, if something activates or not depends on its size and also on its hygroscopicity. So you could think mineral dust particles, and I will talk more about mineral dust later, mineral dust is not hygroscopic, so maybe it doesn't participate in this activation, but that is wrong. And if you want to convince you can just go to literature and look at that paper by Karudas et al. From 2009. There's other stuff, but mineral dust particles act as CCN, and all of them do, basically, or most of them at least. So, now we have our particles in our droplets. The air parcel in the cloud rises further. It gets colder, and once it's below 0 degrees Celsius, we have supercooled droplets. And what then happens if it's cold enough, if an ice nucleating particle was included in a droplet, is whoop, you can have some droplets freezing. That's then a heterogeneous ice nucleation taking place. Why is that important in a cloud? This starts a whole series of other things. So first of all, as long as the relative humidity is high enough, so it's above 100% for water, droplets and ice will grow. But there are regions where the relative humidity is below 100% for water, but above 100% for ice still, and the ice then grows on the expanse of the water droplets. And these ice crystals become large relatively fast, several microns or even larger. They can collide, form aggregates, they can hit droplets, they can splinter from new ice. So all of that chain, I'm not going into that, I just want to show you that that is offset by the very first ice formation, and in the end may lead to precipitation. So all the precipitation we have here in our latitudes is formed via the ice phase in the clouds up there, and depending on outside temperatures we have down here, it either melts on its way down or not. So that is why this first ice formation is really important, and it is also important for radiative properties of the cloud. The cloud scatters light differently depending on if it has ice or not and how much ice is in there. So this is all about emergent freezing in mixed phase clouds. There are also ice clouds, cirrus. So if clouds form below minus 38 degrees Celsius, they are purely frozen. These things high up in the atmosphere, these very opaque things, whenever you see them, you know it's all ice. And for them, homogeneous freezing, the freezing of pure solution droplets can occur. That's what I told you about in the beginning. They more look like that, by the way, and at least as a sketch. For them also, radiative effects are influenced by the presence of how much ice is there. Ice can form in both ways, homogeneously and heterogeneously. Different heterogeneous freezing processes might play a role, but I'm really in my talk focusing on emergent freezing. That is important for those mixed phase clouds. So that was the first part. I'm coming to a very brief historical overview and will explain you a little bit about measurements. And I know there's way too much text on that slide. Just pretend I'm an historian for 2 slides. So, and actually, the first paper, at least that I know of, is by a guy called Vonnegut from 1947, and he describes that silver iodide, when he put that in a Wilson chamber, produced ice crystals. And I have that little asterisk here because he has a brother who wrote a book that's called Cat's Cradle. And for those of you who don't know it, if you can bear dark humor, kind of go ahead and read it if you like fiction, because he kind of mocks the research his brother is doing in that book very, very badly. So anyway, already back then you had people flying expansion type chambers on aircraft. Expansions were done to cool a chamber down, you let in air. Then ice could form if the conditions were right, and the detection limits, the old ones, very often were they let just settle ice crystals down on a piece of paper, took that out and counted how many crystals they had. It's really great. So we can do a bit better these days, but it's amazing what those folks already could do. There were others that used, for instance, injection chambers, cold chambers, where you inject a hot air stream and you have some mixing, and then you can get supersaturation, droplet formation, and freezing if the whole thing is cold enough. A lot of that was done aiming at artificial cloud seeding. That was the thing back in those days. Already in 1962 in a book, there is a parameterization by Fletcher, who really parameterized how many ice nucleating particles are ice active at which temperatures in the atmosphere. I mentioned that because I will come back to that later, and it's used in some models still up to these days. And in the search for the source of ice nucleating particles in the atmosphere that people had really found, some people went out in the field and just measured everything. They sampled lakes, seawater, air, precipitation, vegetation, whatever is there, to find out what stuff it would be that makes ice. And here I want to mention a few names because they have really a lot of literature out, particularly in the 60s and 70s. That's Schnell and Wally. Maybe I should have put it the other way around. Wally was Schnell's boss at one point. Rosinski and Big, so those are the old guys doing a lot of research back then. One thing they found was that biological particles act as ice nucleating particles. So in a paper by Schnell and Wally in 1972, they describe a bacteria called Pseudomonas syringae that can make ice. And I'm mentioning that here because that thing also is out there on crops. And when it is there on crops, if you have temperatures a little bit below 0 degrees Celsius, let's say -2 or -5 or something, this bacteria can nucleate ice, and that can cause damage to crops. So there was an interest to maybe hinder that, and this was the first gene manipulated substance that was actually brought out in field experiments. So they found the gene that makes a protein that makes the ice, and they cut that gene out. And so that really became a test case for how gene manipulation has to be done or also treated when you want to do field experiments. There were a lot of protests back then. I think this is quite interesting, so I thought I should mention that. So the other thing that was already also very well known back then is that mineral dust particles are good ice nucleating particles. Back then people thought it were clay minerals that did it. That can be found in literature, and I mentioned this Popacher and Klett book here, so for people who are just interested in the matter, the book was first published 40 years ago, but it's still readable. I mean, we know more than it's in there these days, but still, again, amazing what those old folks already knew. In 1997, there's a summary by Soma and Savatsky on biogenic and anthropogenic ice nucleating particles, but that came around and was published in a time when not much research on that topic was done at all. I think those old folks in the 60s, 70s had promised we can make rain. There was this drought in the Sahel zone and they couldn't make rain, so kind of there were other promises that were not held, and the funding just vanished and people just went into other fields. But still, that person, I mean, she did a really, really good overview of what was known back then. And also, as I'm still in, so history, I mean, this is now a bit vague because Paul de Motte is still here around and doing research, but he is one of the guys who's always been faithful to research on ice nucleating particles. He did measurements when almost no one else did. And I'm totally sure I forget people here, but those are the papers or the people who published a lot of the literature in the field. This is why I wanted to mention them. So have one very short remark. So then, after a time when not much research was done on ice nucleating particles, a lot of activities came about again roughly 10 years ago. And there are reviews in 2012, kind of summarizing, I mean, a lot of the old stuff. But since then, a lot of new stuff has been found. There's a new publication that just came out last year that only summarizes kind of stuff that was done in the last 5 to 10 years. And it's still a long paper, or already a long paper. So that kind of, I mean, what you know now is there was a lot of stuff already done in the old days. Now I will tell you a little bit about measurements that are being done these days, and then I will go in more detail on new findings. My interpretation is that the field moved on in other research areas and people were looking for things they could do. So the CCN I mentioned before, hygroscopic growth and activation, that Frida mentioned that I did a lot, that was done by the year 2000, roundabout, a bit before that, a bit after that. And instrumentation advanced and measurements became more easy in the year 2005. Particularly, there was an instrument available that you could buy at a company. And so that was kind of, there was a big knowledge jump in that section, and people then tried to do other things. That's my personal interpretation. At least that's what happened in our group. And then after we did the jump, we realized, oh, many other people also changed into that field. So I think that's probably what brought it all about. Or at least part of what brought it all about. So that's all you're going to see about LACES. Sorry, Frida. So LACES actually is a laminar flow tube with which I've been working a lot. And what I want to show you on that site and on that page in general is that there's a variety of in situ measurement instruments. In situ meaning that you have instruments where the air is dragged in. And then the same happens in the atmosphere. You have single particles that are activated to droplets that are cooled down, and at the outlet it is measured how many of those droplets froze at the outlet temperature, so to speak. And we can do that with our flow tube. It's just not transportable. When we do that, we use like 7 meters long tube version of that. So we mimic the atmosphere. It can be done in these continuous flow diffusion chambers, CFDCs. That's the type that Paul DeMott, the person I mentioned before, has been using first, and now there are different copies of that around called pink, zinc, kink, spin, whatever, and always an IN in there. And so they have single particle detection. They are really close to what happens in the atmosphere. They have a good time resolution, but they also have a pretty high detection limit. So unless you have a lot of ice nucleating particles in the atmosphere, you aren't going to see anything with them. And also they are really difficult to operate. So they have good and bad sides. And the thing is, because they have these high detection limits, they typically in the atmosphere can only measure at relatively low temperatures, let's say below -20 or so, or even lower, where you have relatively many things that can nucleate ice. Another principle, and that was around in the old days already too, is cold stages. So here are 2 pictures from our lab. Many people have built something similar like that in the last 2 or 3 years. And what you can do there is you look at macroscopic droplets. You just pipette them onto something or into something. So either here on a little glass slide or here into little tubes. They are arranged in such an array. And then when you have a substance you want to look at, you can just put that in water, mix it, pipette it in there, and look at really large volumes. So you don't have that constraint that you need high concentrations anymore. You also can sample air samples on filters and wash them off. So you can sample for a long time. So you again can increase your concentration in water, but you have a bad time resolution. And you can also sample on filters and then punch out little holes and put them in waters here, in pure water, and so these are all methods that are done. And yeah, but so the advantage is lower detection limit. Disadvantage is contamination. If you have large water volumes, you can use pure water, but you will always get freezing at a certain temperature, way above the homogeneous freezing, because you have some impurity in there. So depending on how large your droplets are, you can only go down to -20, -30 degrees Celsius. If you want to go down much further, you need very expensive equipment. So that's what I wanted to mention about that, and now I go to the findings. And this is what we are first I want to talk about the effect of particle size and or concentration solution. What we look at here is a slab of feldspar. And what they did is they cooled it down. Here you have this type of deposition freezing, like water from the gas phase goes on two sides. As soon as the first ice crystal grew on here, they stopped the cooling. And already after 2 seconds, these things are 5 microns in size. So nevertheless, some more always started to also nucleate ice. You see by the color code how long after the first one the ice was formed. They did a lot of runs to do that. And that particular spot very, very often was the one where ice formed first. And also you see these columns growing out here. So these columns are oriented in a way how a certain crystal phase in the crystal is oriented, but that crystal phase just doesn't show up often when it doesn't show up when you cleave it, not on its own. That's why it only shows up in cracks. That's why they find ice nucleation always on those cracks. And you don't really see the nucleation moment because it grows so fast, but they calculated back where the center of that crystal would have been to find that. So that's one of the first proofs visually actually that I've seen that it's really specific sites on mineral dust particles that can cause the ice nucleation or that are causing the ice nucleation. And when we do measurements, it looks like that. That is now results from LACEs. Frozen fractions versus temperature at which we measured. Sorry, that one is flipped. It's colder towards the right. That is for kaolinite particles or for feldspar particles. And you see for different sizes, like 3, 5, 700, 1,000 nanometers, the signal just increases. The same down here for 2, 3, 4, 500 nanometers, the signal increases. And you can imagine, like, if you have a slab of, let's say, a square meter or so, that's of course now overdoing it. And if you have one ice active site on that, that's ice active at, let's say, minus 30 degrees Celsius, you form one particle of that. The droplet that has that particle inside will freeze at minus 30 degrees Celsius. If you now cut that into that one square meter thing into 100 squares and make 100 particles of that in 100 droplets, only one of 100 will freeze. That's the effect. So if you wouldn't account for the surface area, you would make a mistake. So what you can do, this is the frozen fraction, what we usually measure. That's the number of ice crystals versus all droplets we looked at, frozen or not frozen. That can be normalized with this formula towards the surface area that was included in a single droplet. That's what's done for insoluble particles. You can do this normalization for other means as well. For instance, for amount of precipitation you sample, you have in a drop, or also for air you sample into a droplet. So I'm not going into that. I just want to tell you have to normalize your results in some way. And if you do this, then you see that all the data fall together closer on one line in both of these cases. And bottom line here is freezing dust scale with particle size, because you have these sites on surfaces that are ice active. For mineral dust, it's actually depending on the surface area, and frozen fractions cannot be compared directly unless you compare the exact same measurement, because I will compare frozen fractions in the next slide. So I'm saying that if you have the exact same size in a droplet, you can compare it directly, but usually you have to be very careful. And the surface area has to be determined carefully. So that's the first thing I want you to remember. Second thing is the effect of mineral composition. So what we have here now is, again, frozen fraction. All of those have 300 droplets that we looked at had 300 nanometer particles in them. For different mineral samples, what I should mention is if you buy a sample that's called illite, it's typically not pure illite, it has some contaminations in it. And those samples we looked at had different amounts of potassium feldspar in them. And I've kind of arranged them here in the same manner they are arranged in here. The one with the highest potassium feldspar content froze at the highest temperatures. And feldspar is a primary mineral, so if the rock or the material from the mantle cools, that's what you get. But if it's weathered, that's a process called hydrolysis, then it is weathered to form clay minerals. And the fact that potassium feldspars are really good, as INP was already said by Atkinson in a paper by 2013. We did what I'm showing up here a year later. It has been corroborated by others. It's not totally nailed down, but I think it's very likely that the feldspars play a much larger role than the clay minerals, because what we also did in that study is we coated our particles with sulfuric acid. And the coating itself, once we have a droplet, doesn't play a role anymore. The sulfuric acid just dissolves in the huge droplet around our particle. But all the ice activity collapsed onto one line from all of those different minerals. That means we kind of try to mimic this hydrolysis process and manage to destroy the ice activity. So the feldspar basically was destroyed in what we did. And we call that the remaining clay baseline, because that's also where clay was that had no feldspar in it. And also I want to point out that the atmospheric relevant particles size that we used at that the mineral dust particles activate at below -20 degrees, no matter how much feldspar they had in them. So that's a typical temperature range for mineral dust to activate ice. So potassium feldspar content might be a determinant factor. Next, biological particles. I mentioned that already last century they knew that bacteria, pollen, fungal spores and other things make ice, but they are comparably large. They are tens of micrometers in size. So they typically have a low residence time in the atmosphere. They are there, but not so many. But I also told you that this one bacteria, there are more than only one that make that, but for the bacteria it was known you have a gene that makes a protein, and that protein complex, and that nucleates the ice. That is embedded in a membrane for bacteria. For pollen and fungal spores, it's a relatively new discovery that there are ice nucleating active macromolecules that can be washed off. You can take a spoonful of pollen in water, filter it so the pollen is retained in the filter, and then the water that comes out has everything soluble from the pollen in it. There are other sugars and fats, and also some sugars, polysaccharides that can nucleate ice. And the same is true for fungal spores too, only here it's proteinaceous macromolecules, some proteins. And if they now can be washed off, they don't have to be on their original carrier anymore. That's interesting because it changes how often they can occur in the atmosphere. So just a little side remark is that we were actually able for all of those to derive ice nucleation rates for single macromolecules. That's now a bit off topic and I'm not going much more into that, but what I want to show you is that plot that is in this one paper, where you here see the size of the macromolecules in kilodalton versus the temperature where they are ice active. It's like if you have a curve, it's like where half of them are ice active. And this blue curve here goes back to what I showed you in the beginning about homogeneous freezing. That is the size of this little ice embryo that is needed. I showed you it was temperature dependent. And you see that that aligns quite well. So what happens when you have such a macromolecule is you have that molecule, and it might have an extension or not, but water molecules seem to arrange all around it. And then this whole clump is the ice germ, the original one. So you don't have to fill up all the void with water molecules. Is at least what I imagine. I could be wrong, but it follows really this trend really well. What I want to mention too is that also in seawater there are macromolecules that can nucleate ice. So that is again frozen fractions versus temperature for a lot of surface microlayer samples from the ocean. Red is Arctic and the yellow one were, no, it's all Arctic, but sorry. So anyway, some were further north than others. So the more red ones were further north. And when you normalize this to the total organic carbon, still, I mean, there's a spread and some are more ice active, but all of that is still there no matter if you look at the surface microlayer, pure or filtered to below 200 nanometers. So there are also macromolecules there that make the ice. And it's also seen in the air. So I told you bubble bursting brings up sea spray into the air. So some of that stuff also seems to be put into the air. That's a measurement by Paul de Motte. Part of that, the blue symbols are done in the air measurements. The red ones were done at a wave tank. The green ones are in the wave tank when there was an algal bloom. So it really seems these ice nucleating macromolecules in seawater come from algae. And when you compare that to what he finds in air in North America on a continent, it's low. but it still can be of importance if you are far out somewhere in the remote ocean areas. So, ice activity in microorganisms comes from macromolecules, and I didn't point that out clearly, but it usually happens at relatively high temperatures, from -2 down to -20 degrees Celsius. Now, if you mix the two, biomaterial and mineral dust, that is one thing that we did in our lab. So here's a few measurements. We had more, and then we derived that line and just made a few check measurements. This is where light particles would activate ice. Again, it's all the same size, 500 nanometers particles in that size. In that case, here is where pure pollen washing water particles would make ice. So we washed off the stuff, made particles, looked at how well they made ice. If we mixed illite and pollen washing water, we got that line here. It follows the green one and then has a little increase here in the end. So it's a bit lower than the green one because we made sure that every particle has an illite core and pollen washing water around it. So a 500 nanometer particle will have less pollen material than a pure one. That is why that curve is a bit lower. But when such a mixed particle has an ice nucleation active macromolecule in it, it makes ice at the same temperature where the pure bioparticles would make ice. So one macromolecule is enough, and I should mention on one pollen there can be thousands of these macromolecules that can make ice. It was also shown in many other publications in the last few years that that soil dusts really are, when they are ice active at high temperatures, that comes from biological material that is on them. You can easily find that. You measure it, then you heat it. Heat typically destroys at least the proteins. If you then measure it again and it is not ice active anymore, you know it came from bacterial matter, and that has been really done a lot. So, in mixtures of mineral dust and ice active biological matter, the latter causes the ice nucleation, and it also means there can be way much more of that stuff out there than only the original carriers. Ice activity of ash. So that's going to be a relatively short thing. I only want to mention one thing to you here. When you combust liquid fuels, what you're basically doing is you turn carbon to carbon dioxide that becomes gaseous. But if you don't do that completely, you get soot particles over here. Carbonaceous soot particles from incomplete combustion. If you, however, burn solid fuels, wood or coal, and you don't burn it completely, you get the soot particles too, but you also get ash particles. All that inorganic material in your fuel has to go somewhere. That forms ash particles. So there are two things, soot and ash particles. They are not the same. And I here went back to that overview paper. Actually, I'm a co-author and I kind of did that plot. But so when you go to literature, you find a lot on soot and almost nothing on ash. And on soot, this plot here shows you at which relative humidity and at which temperature a certain fraction, like 1% or 1 per mil of all particles that were observed make ice. But the point here is that all happens at comparably low temperatures, and I told you I'm only looking at mixed phase clouds. So I'm not saying anything on soot and cirrus clouds. I can't, I don't know anything, but this plot isn't relevant. This plot is still quite a mess too. I mean, there are the red and gray data here are the ash data. And yeah, you could say, oh yeah, there's a trend, but if you really look at the scale, there are orders of magnitude in between. Then there are some soot data here, some over here. If something looks messy like that, I'd say we haven't understood some very basic fundamental things yet. Oh no, it wants to restart. No, pick a time, yeah. Pick a time. I just say tomorrow, okay? And now? Close it, okay. Yeah, so where was I? Yeah, so that is a big mess, and I would wish I could tell you something, but we are still working on this ash stuff at least, and we haven't really managed anything. So I have to leave you here with contribution of ash or soot particles to atmospheric INP remains an open issue. I will come back to that point, however, at the end of my next section. I will hurry up a little bit, but I should be able to show you everything I want to. So, because the next section is atmospheric INP concentrations. So I told you about different materials in the lab and how well they make ice and what we learned about them. That's all very exciting, but if you want to tell a modeler what he or she should use in their model, we are missing one thing. We can tell you, look, this stuff is important, but we cannot tell you how much is out there. So one way to go would be to really characterize every material you can think of as being ice active and also find out how much is there in the atmosphere, and that's not possible. So there have to be workarounds, and one workaround was found again by Paul de Motte, or suggested. So he says just simply go out there, measure how many particles there are that are larger than 500 nanometers in size, and then from that number take a certain temperature-dependent fraction and assume that is how many ice nucleating particles you have out there. Don't care about what it is, we just say as long as it's large, it might be an ice nucleating particle. He compared observations to the predictions. Of course, I mean, he fit that line so that it fits. But still, I mean, yeah, there's quite a good correlation there. By now, there are several different formulations of that parameterization, but that could be one way to go. I actually think it's not such a bad idea. But yeah, I don't know how many different formulations we would need for different air masses. So that's an open issue. Another solution was done by the people in Leeds. They said, let's pick a few things that we think are very important, and for their study, they simply used feldspar and the marine aerosol particles that they just had measured. So they come up with maps like that one, where the black contour lines give you the IMP concentrations from feldspars, and the reddish ones give you the concentrations from marine bioparticles. There are a lot of assumptions behind that. And for their example also, it showed that improving the marine, including the marine particles improved the comparison with measurements of atmospheric IMP concentrations. I don't think they are there yet, but this might be another way to go, actually, like really focus on the most important components, although I can't tell you yet which ones those would be. To give you an overview of what we are dealing with, these are measurements of precipitation samples mostly taken in Northern America and Europe. And this gray area here encircles the area where the results were. And they translated the INP per volume of precipitation to INP per volume of air. So between these axes, there's a lot of arguments in the paper why you probably can do it or why your error isn't too large. So, but we see the typical thing that has been seen already by the old folks last century is there is an increase in INP number concentration by about 1 order of magnitude every 5 degrees Celsius decrease. That's really strong. And also at any one temperature, we have quite a spread. And from what I've told you before, the assumption would also be, I mean, you see that interesting dip here. Probably all of that is caused by biogenic materials. That is caused by mineral dust particles. That is one assumption. So that's what we have to deal with, and we have to find ways to kind of parameterize that. And so in the old days, that is the Fletcher curve. I mean, that it was just parameterized by a single, oh, well, okay, I should say the Fletcher curve can be shifted. It has a parameter in it that you can just change, then you can just put it everywhere. But that's a very common formulation. And so I could have put that in here. You will see that later in the next plot, so that would be there. So this now compares that old Fletcher curve to recent measurements that a colleague of mine did with filter samples from Cape Verde, 4 years of filter samples. Additionally, 2 months of CFDC measurements. These are the filter sample results. These are the CFDC results. You see one is only measuring in the high temperature range, the other only in the low temperature range. But what he says is there's quite a variation on very short time scales that you get with the CFDC measurements that you don't see in the filter measurements because you average over 2 to 3 days in that case. And he tried to correlate that to a lot of different parameters and didn't find anything that was correlating with it. He also found that that was log normally distributed actually. So you could really, instead of just putting a line here, you could put a distribution on top of it, interestingly. So I don't know if that's going to help any, but it's a very, very interesting finding. And now is the question, do you give me 5 more minutes or should I come to my, yeah? I have 5 more minutes because this is now, Mm. About atmospheric INP concentrations that I've been measuring. I told you I've been in the lab for most of my life, so now I'm going out into the field. That's the next thing. Now people have worked a lot in the lab in the last few years. Now we are all going to the field. And we've sampled filter samples in Beijing, November and December 2016. Like this is Beijing, like you see all those highway rings, and this is where the university there is. And it was really interesting. We had a few phases when air came from north with high wind speeds, and we had clean phases, but we also had a lot of phases, typical winter Beijing air, that was very dirty. So there's a factor in total, no, not in PM 2.5 mass concentration, so all particles up to a size of 2.5 micrometers. Factor between clean and dirty was roughly 30. So we had really two different, completely different types of conditions. If you now measure, you can get frozen fractions. In this case, I converted it to number concentration per liter of air again versus temperature. You get these curves. They are color-coded with respect to PM 2.5 mass. And as you see, you don't see a trend. So it really looks very messed up. And what I did now for the next slide is cut through here, take all those values and correlate them to the PM 2.5 mass concentration, and you see there is no correlation. I mean, this line isn't in there because I want to imply a correlation, but because I want to imply no correlation. If you look at the fit parameters, it's totally clear. And we have done that with a lot of different parameters. We've looked at like carbon concentrations, total number concentrations, particles larger than 500 nanometers. That goes back to the de Motte parameterization, also the two de Motte parameterizations. No correlation. That's now not saying the de Motte parameterization is wrong. It's just saying we have so many large particles in Beijing, 500 nanometers and larger, that are brought in there by air pollution that are not ice active, that this correlation just can't work. I mean, the parameterization isn't done for those purposes. So our conclusion from that is that anthropogenic pollution in Beijing did not add ice nucleating particles, at least not down to minus 25 degrees Celsius where we had valid measurements. And here is now again, so this is the zoo of measurements I showed you before, only all in green. This is some more we did with the second instrument. This is the Fletcher line again. The background is the background from the Peters parameterization. You see our Beijing air lies right there in the middle. So I think it's really quite fair to assume we did not add INPs through all the combustion processes that are ongoing in Beijing. We just did not add anything. And here now that becomes very speculative, which is why I used such a very light color here. I had seen a poster last year on a conference where the British people in Leeds, during a night they call bonfire night, they seem to have large fires during that night, they made continuous measurements on filter samples, analyzed them for ice nucleating particles, didn't find any increase during that night. So that was also going in the same direction. I've talked to colleagues from Frankfurt who measured in the exhaust of an airplane, like for Lufthansa somehow, and they didn't find ice nucleating particles there, and they also did not find them in the Amazon when comparing dry and wet seasons. We made measurements on ships and aircraft in the last year, and sometimes we had like a discriminator that blocked out or that didn't sample when there was air coming from airport or from the ship engine, or sample on specific filters. No influence. Also, I have data from the Arctic that imply there is no influence from soot or ash particles there. So this is really very light green. This is all totally preliminary. Don't cite me on that. But I would actually, I'm not betting usually, but I'd be really willing to bet on that in 5 years we say that soot and ash particles do not add INP to the atmosphere. But as I said, I can be wrong, really. It's just my feeling. So in summary, now I've read out through you all of that one now. I kind of added, before there were some dots, with indications for soot and ash that it might not contribute, at least in mixed phase clouds. I did not talk about those low temperatures where cirrus clouds occur. And then I didn't really tell you this in detail. There's a suite of different measurement techniques for different applications. And so we've done a lot of comparisons in the community, and we seem to have a good handle on which instruments do what, why, and why they work or don't work under certain conditions. So now it's the time to thank a lot of people. So this is the group I'm working with, and it's a great group, really, all of them. Those people that have a circle around them are those people with whom I've worked at LACES for the past years. So there's Dennis Niedermeyer, Susanne Hartmann, Frank Stratmann, Steffi Augustin Bautes, and Sarah Grave. And I'm really grateful to have been part of that group, of like the whole cloud group. And also I'm grateful for the DFG for funding INUI. That's the German research unit 1525 that unfortunately is just running out. So it funded me the last 6 years, and I now have to look for new things to do. So, and with that, I thank you for your attention.
Thank you.
You're welcome.
And if you want to come, we have a bonfire night here in Sweden on last of April. If you want to come and measure and see how our ash and dust does as INP.
Okay,
Do we have any questions?
Mm-hmm.
Thank you, Heike. That was a really nice overview. I think it's...
Oh, I thought for you it was all known.
No,
Anyway.
no, well, yeah, to some extent, but
Yeah.
not as
Anyway.
nicely presented and
Thanks.
summarized.
Mhm.
It's just I don't know, the people in Leeds, they have parameterized and sort of assumed that feldspar and marine organics can explain most of the INP concentrations, and it looks quite good when you see their model simulations, but then you see the results that you presented from Andre Velti, and you see no correlation with dust. So how do you...
Okay, I should have been more precise. So what he looked at different chemical compositions or compounds, so that did not correlate. He does see that when there is a direct influence from the desert, he does see a signal. So that is true. He makes this, he distinguishes between marine when there is some kind of a background and then dust. But he also says because he has that integral of 1 to 3 days, that signals kind of are washed off in what he's measuring. Because I mean, yeah, you would have 3 days dust straight to not get an average.
So you can make the two pictures.
So there should probably be
good,
that distinguishing between these two at least. Yeah.
And maybe a follow-up question on what do you think is missing in the parameterization, like from the Wilson et al.
I mean, if you look, I mean, there is another paper where they picked that up, the Jesus, I can't pronounce his last name, paper, and so it seems to do a quite good job. So I wouldn't know what to add. They don't have the biology components from land in there, so that would be probably one thing that could be used. Because they are like these huge land masses, and they will become ice first and thus settle out of a cloud first as precipitation when there's some. So that might be missing on continents is what my guess is. And for the sea spray, I mean, we are looking into that right now to see how airborne that can really get. That is one of these assumptions they have in their calculations. So, I mean, maybe they already solved the puzzle. I'm not sure. I just think this is where people are looking at right now, how good that is and what is missing. Sorry, I don't have an answer.
No, that's...
I can ask a general question, which is how does lab compare to reality? So specifically, were you talking about the mineral dust and how you have these sites, but then as soon as you coat with sulfuric acid, then you just follow on that one line. So what's realistic? How often do you have like clean mineral dust flying around in the atmosphere?
Yeah, that is what I tried to do with this one slide where I said we could go out and measure every little detail and really also tell how much of that is there, and I don't just simply think it's possible. I think the role that the lab had in the last years was to point towards, for instance, like potassium feldspar is important instead of clay minerals, which were used before, or also to say, yeah, the bioparticles, there isn't only these big bioparticles. There's a paper that says, okay, the stuff falls out and then it doesn't play a role at all. That might be totally wrong. It is wrong. So, so that was what the lab was good for. It was also good for all those comparison studies that I did not talk about, to learn how our instruments really function. But yeah, for the atmosphere, like all that detailed lab work is really hard to transfer directly, I'm afraid. So yeah, that's
so now we're all going out in the field.
that is why now, I mean, you follow up on your question, what happens afterwards? Now people have done a lot of laboratory measurements in the last years, and you can still do very fundamental stuff, basic understanding, but a lot of people who did lab studies in the last years are now going to the field. It's a real big movement these days.
So over land then, is it mostly the feldspar? Because you talked also about the macromolecules sticking to other particles and things like that. Is there some sense for what the split there is, or?
There must be bioparticles on land that are responsible for ice nucleation, because we do see ice glaciating at high temperatures, like -8, -10 degrees. Sometimes they are totally glaciated already, and they never got any colder or didn't get seeding from above. These are all things that also can happen. So, but the thing really is there are so little of them there. I didn't mention that number, but oh no, I blew it. Anyway. Connect, maybe. Yeah, that plot that I showed you with this, the background the precipitation samples, you have 1 in a cubic meter of these particles that are ice active at these high temperatures. And it's very hard to find them. And typical aerosol concentrations are such, thanks a lot, are such that at -20 degrees Celsius, 1 in a million aerosol particles that you detect is ice active. And it's hard to get a handle on them. We can say they must be there, but it's totally hopeless also to detect them chemically. It just won't work. That is the point I was referring to. At -20, like in this range, you have a million aerosol particles, typical rough. Okay, they are varying too, but it as a rough rule of thumb, and like 1 of them is ice active, and above that it even drops down much more. So they are there, but you cannot really pinpoint them on a filter. Although there's a paper by Hill et al., and that's actually funny. They had these tubes, and then they picked the tube that froze the first and thinned it down, distributed it, picked the tube that froze the first, did that until they only had a little clump of material left, which they then photographed. So yeah, people are working in that direction, but yeah, there's work to be done.
More questions? Or shall we thank Heike again for a really nice presentation?